This is the third module of chapter 8. Also, this is the last module of this chapter. So far in this chapter, we have discussed algebraic elements, minimal polynomials, and characterized the simple algebraic extensions and simple transcendental extensions. In this module, we will consider the extensions f by k such that every element of f is algebraic over k. Here we show that every finite extension is an algebraic extension, and our most known extension C by R is an example of an algebraic extension. We will conclude this module with the characterization of simple algebraic extensions. Now, let us define algebraic extensions. A field extension f by k is called an algebraic extension if every element of f is an algebraic element over k. That is, if for every C belongs to f, we have some non-constant polynomial f(x) over k, of which C is a root. Otherwise, the extension f by k is said to be transcendental. Equivalently, if some element of f is transcendental over k, then f by k is called a transcendental extension. As an example, we have C by R, which is an algebraic extension. If A plus IB is an element of C, you know that A plus IB is a root of the real polynomial x minus a whole square plus b square. But the extension R by Q is an transcendental extension because there are elements E pi in R, also so many other elements which are transcendental over Q. Note that there are many elements in R, for example root 2, cube root of 2, etc., which are algebraic over Q. Still it is an transcendental extension because all elements of R are not algebraic over Q. Now we show that every finite field extension is an algebraic extension. Consider a finite field extension f by k. Assume that the degree of the extension is n. Now we show that every element of f is algebraic over k. For this, consider an arbitrary element C from f. Since dimension of the vector space f over k is n, no set of more than n elements in f can be linearly independent over k, and so the set 1 c c square up to c to the power n cannot be linearly independent, and hence we have n plus 1 elements k0, k1, so on kn in k, not all 0, such that k0 plus k1c plus so on plus kn c to the power n will be 0. Thus we get a non-zero polynomial f(x), namely k0 plus k1x plus so on kn x to the power n over k, such that fc equal to 0, that is, c is a root of this non-constant polynomial f(x) over k. Hence it follows that C is an algebraic element over K. Since C is an arbitrary element of F, it follows that every element of F is algebraic over K, and hence F by K is an algebraic extension. Now, it is natural to ask whether the converse of this result is true, that is, whether every algebraic extension is finite. Here we give an example to show that the converse is not true. For this, consider the field F, which is generated by all root P, where P is a prime number over Q. Then we can show that root 2 does not belong to Q and root 3 does not belong to Q root 2, and so on. And thus it follows that Q is contained in Q root 2 properly, and Q root 2 is contained in Q root 2 root 3 properly, and hence we get a strictly ascending sequence of subfields of F. Thus, it follows that F by Q, the extension F by Q, is an infinite extension. Now, we show that this extension F by Q is an algebraic extension. For this, consider an element A from F. Then it is easy to observe that A will belong to Q root 2 root 3 so on root over P n for some prime P n. Here actually P n is the nth prime in the sequence 2, 3 and so on of all primes in ascending order. You know that the degree of the extension Q root 2 over Q is 2, the degree of the extension Q root 2 root 3 over Q root 2 is 2, and so on. Thus, the degree of the extension Q root 2 root 3 up to root over P n over Q will be less than equal to 2 to the power n. That is, this extension Q root 2 root 3 up to root over P n by Q becomes a finite extension and so algebraic. Thus, the element A becomes algebraic over Q. Since A is an arbitrary element of F, it follows that the extension F by Q is an algebraic extension. Thus, we get an example of an algebraic extension which is not finite. Now, we characterize those algebraic extensions which are finite. In this regard, our first result is this, which states that an algebraic extension F by K is finite if and only if F is equal to K C1 C2 Cn, that is, a field generated by C1 C2 Cn over K for some C1 C2 Cn belongs to F. For the proof, first assume that the extension F by K is finite. Then F has a finite basis over K, say C1 C2 Cn, and hence every element of F can be expressed as K1 C1 plus K2 C2 plus so on Kn Cn for some suitable k1, k2 up to kn in K, and hence it follows that K is the field generated by C1, C2 up to Cn over K. For the converse, let F is the field K C1, C2 up to Cn for some C1, C2, Cn in F. We show that the extension F by K is finite. First note that since F by K is an algebraic extension, these n elements C1, C2 up to Cn are all algebraic over K. Let us denote the minimal polynomial of Ci over K by mix and assume that di is the degree of the polynomial mix. Since Ci is algebraic over K and K is contained in K C1, C2 up to Ci minus 1, Ci is also algebraic over K C1, C2 up to Ci minus 1, and also we have that the minimal polynomial of Ci over K C1, C2 up to Ci minus 1 is a factor of mix, and it follows that the degree of the extension of the field K C1, C2 up to Ci over the field K C1, C2 up to Ci minus 1 must be less than equal to di. Thus, by the tower rule, we get K C1, C2 up to Cn over K is equal to the product of these degrees of extensions, which is again less than equal to d1, d2 up to dn, and hence it follows that the extension F by K is finite. As an immediate corollary, we have these beautiful equivalent characterizations. Let F by K be a field extension, C1, C2 up to Cn are elements of F. Then the following conditions are equivalent. The conditions are that K C1, C2 up to Cn over K is a finite extension, and this extension, our second condition is that this extension is algebraic, and our third condition is that the elements C1, C2 up to Cn are algebraic over K. Here we prove that 1 implies 2, 2 implies 3 and 3 implies 1. 1 implies 2 follows from the result that every finite extension is algebraic, and 2 implies 3 follows from the definition of algebraic extensions, which states that every element of K C1, C2, Cn is algebraic over K, and since C1, C2, Cn are elements of K C1, C2, Cn, it follows that C1, C2, Cn are algebraic over K. And in the previous result, the proof we have followed using a similar proof, we can show that if C1, C2, Cn are algebraic over K, then the extension K C1, C2, Cn over K is finite. Now, our next characterization of the algebraic extensions is that if F by K is an algebraic extension and it has only finite number of intermediate fields, then the extension F by K is a finite extension. To prove this, first we show that this extension F is of the form k C1, C2 up to Cn for some n belongs to n, that is for some natural number n, and C1, C2 up to Cn belongs to f. On the contrary, if possible, assume that this is not true. Then we have an infinite strictly ascending sequence of intermediate fields k subset of k C1, which is again a proper subset of k C1, C2 and so on. Since this is an infinite sequence and strictly ascending, thus we get an infinite number of intermediate fields, namely k C1, k C1, C2, k C1, C2, C3 and so on. This contradicts that the extension f by k has only finite number of intermediate fields. Thus, f equal to k C1, C2, Cn for some n belongs to n and C1, C2, Cn belongs to f. Since C1, C2, Cn are all algebraic over k, it follows that f by k is finite. As an application of the corollaries we have proved just now, we show that the set of all algebraic elements form a field. To state formally, let f by k be a field extension, then the set L of all algebraic elements of f over k is an intermediate field of f by k. First, to show that k is a subset of L. For this, note that every k belongs to k is a root of the polynomial x minus k in kx, and so it is algebraic over k. Thus, it follows that k is a subset of L. Now, consider a b from L, of which b is non-zero. We are to show that a minus b and a b inverse also belong to L. Since a, b are elements of L, they are algebraic over k, and which implies that the extension KAB is an algebraic extension over k. Since KAB is a field and AB belongs to this field, we have A minus B and AB inverse are elements of KAB. And since KAB by K is an algebraic extension, it follows that A minus B and AB inverse are also algebraic over K. That is, A minus B and AB inverse belong to L. Thus, it follows that L is a subfield. Recall the definition of algebraic numbers. A complex number z is said to be an algebraic number if it is an algebraic element over Q. So, from the previous result, it follows that the set A of all algebraic numbers is a field. Now, we characterize an algebraic extension f by k in terms of intermediate fields L. We show that f by k is algebraic if and only if both the extensions f over L and L over k are algebraic. Recall the tower rule, which states that the degree of the extension f over k is the product of the degrees of the extensions f over L and L over k. This is a similar result. So, let us now state the result. Let f by k be a field extension and L an intermediate field of f by k. Then both f by L and L by k are algebraic if and only if f over k is so. First, assume that both f over L and L over k are algebraic extensions. We show that the extension f over k is an algebraic extension. For this, consider an arbitrary element A from F. We are to show that A is algebraic over K. Since F is an algebraic extension over L, so A is algebraic over L. Suppose that mx is equal to x to the power n plus L1 x to the power n minus 1 plus so on plus Ln belongs to Lx be the minimal polynomial of A over L. We can consider this polynomial mx as a polynomial over the field k L1 L2 up to Ln, and hence it follows that A is algebraic over k L1 L2 up to Ln, and then we have the extension k L1 L2 Ln A over k L1 L2 Ln is a finite extension. Again we have that the extension L is algebraic over k. Since L1 L2 Ln are elements of L, so L1 L2 up to Ln are algebraic over k, and this implies that the extension k L1 L2 up to Ln over k is a finite extension. Thus, by the tower rule, it follows that the extension k L1 L2 up to Ln A is a finite extension of k, and since every finite extension is an algebraic extension, it follows that A is an algebraic element over k. Hence, we have the extension f over k is an algebraic extension. For the converse, let f over k be an algebraic extension. We show that the extension L is an algebraic extension of k, and the field f is an algebraic extension of L. For this, consider an arbitrary element A from L. Since every element of F is algebraic over K, so A is also algebraic over K. Thus, every element of L becomes algebraic over K, and hence the extension L over K is an algebraic extension. Now, to show that F is also algebraic extension of L, and for this consider an arbitrary element A of F. Let Mx belongs to Kx be the minimal polynomial of A over K. Since K is a subset of L, we can consider Mx as a polynomial over L, and thus we get a polynomial Mx over L, of which A is a root, and hence A becomes algebraic over L. Thus, F becomes an algebraic extension of L. Now, we prove a necessary and sufficient condition for an algebraic extension F over K to be simple. Recall that an extension F over K is said to be a simple extension if we have some C in F such that F is equal to Kc, that is, F is generated by C over K. Simple algebraic extensions are very important in the theory of fields. That is why this is not the only result characterizing simple algebraic extensions. In future, in the later modules, we will also characterize simple algebraic extensions. Now, let me state the result. Let F be an algebraic extension of an infinite field K. Then, the extension F over K is a simple extension if and only if it has only finite number of intermediate fields. Though we are proving the result for a special case considering K to be infinite, still I would like to point out here that this result holds for finite field F also, which we will prove in the finite field module. Now, let me prove the result. First, assume that F is a simple extension of K, that is, F is equal to Kc for some C in F. Let Mx be the minimal polynomial of C over K. We are to show that it has only finite number of intermediate fields. Suppose L is an intermediate field of the extension F over K. Then C is algebraic over L, and the minimal polynomial Fx over L divides Mx in Lx, and so in Fx. Also assume that Fx is equal to x to the power n plus L1 x to the power n minus 1 plus so on plus Ln, and denote L dash is equal to K L1 L2 up to Ln. Then Fx can be considered as a polynomial over L dash. Since L dash is a subfield of L irreducibility of f(x) over L implies that f(x) is irreducible over L dash. Otherwise, f(x) would be reducible over L, but which is not so. Since f(x) is irreducible and monic, hence f(x) is the minimal polynomial of C over L dash. This implies that the degree of the extension L dash C over L dash is equal to the degree of f(x), which is again equal to the degree of the extension of LC over L. Now, f equal to Kc implies that f equal to LC is equal to L dash C, and hence it follows that the degree of extension of f over L is equal to the degree of the extension of f over L dash, and which is equal to, by the Tower rule, f over L into the degree of the extension of L over L dash. Then the degree of the extension of L over L dash becomes 1, forcing L to be identical with L dash. Thus, the intermediate field L is determined uniquely by the coefficients of f(x), which is a monic factor of mx in f(x). Since the polynomial mx can have only a finite number of factors in f(x), it follows that the extension f over k has only finite number of intermediate fields. For the converse, assume that the extension f over k has finite number of intermediate fields. Since f over k is algebraic, it follows that f over k is a finite extension. Now consider the set N as the set of all degrees of the extensions of the form Ka over k, where A runs over f. Since the extension f over k is a finite extension, so the set N becomes a subset of the set of all natural numbers. Also, N is a finite subset, since the extension f by k has only finite number of intermediate fields. Thus, N becomes a finite subset of natural numbers, and so it has a maximal element. Say it is Kc over k, where C belongs to f. Here we actually show that f is equal to Kc. On the contrary, if possible, assume that f is not equal to Kc. Then there is some d in f such that d does not belong to Kc. Consider the intermediate fields of the form Kc plus Kd, where k runs over k. Since f by k has only finite number of intermediate fields and k is an infinite field, so we must have some ab in k which are distinct, but Kc plus ad is equal to Kc plus bd. Then we get ad minus bd belongs to Kc plus ad, which implies that d is equal to a minus b inverse into ad minus bd belongs to Kc plus ad. Note that a, b are two elements of k and a not equal to b. So, we have a b inverse and it is in k. Also, c equal to c plus ad minus ad, and hence it belongs to Kc plus ad. This implies that Kc is a subset of Kc plus ad, and not only that, since d is in Kc plus ad, but D does not belong to Kc. So Kc becomes a proper subfield of Kc plus Ad, which contradicts the maximality of Kc over K in N. Thus, our assumption that F is not equal to Kc is false, and it follows that F is equal to Kc, showing F by K to be a simple extension. Thus, we see that an algebraic extension F over K is a simple extension if and only if it has finite number of intermediate fields. In this module, we have introduced algebraic extensions. We have proved that every finite extension is algebraic, and if F over L and L over K are algebraic, then F is algebraic over K. Also, I would like to point out that there are algebraic extensions which are not finite.